Our brains evolve to understand days, seasons, and perhaps a single human lifespan. We are simply not biologically wired to comprehend a timespan of 14 billion years. To actually grasp the true age of the universe, we have to scale it down to a framework our minds can process. Imagine taking the entire history of everything that has ever existed and compressing it into a single 10-minute clock. This diagram shows exactly how that compression works. On this timeline, every single second that ticks by represents exactly 22 million years of cosmic history. If we start this clock at the exact moment of the Big Bang, how long does it have to tick before the first human beings finally appear? To answer that, we have to trace the massive void that comes before us. To understand our true significance in the cosmos, we must first accept how vanishingly small our window of existence actually is. In the beginning, an infinite void gives way to drifting clouds of primordial gas. Over millions of years, gravity acts as a relentless mechanic, pulling cosmic dust together to forge the very first star systems. This diagram shows a star's precarious internal mechanics, a violent standoff between outward-pushing core energy and inward-pushing gravity. When fuel exhausts, energy stops and gravity instantly wins. The core crushes inward, triggering a supernova, an intensely bright explosion expelling its mass into space. These dying stars operate as a cosmic recycling center. As they tear themselves apart, they blast out the complex, heavy elements, like carbon and iron, deep into surrounding space. These stellar explosions scattered carbon, oxygen, and iron into the void. Without these specific heavy elements, the universe would have remained a sterile soup of hydrogen and helium, incapable of forming rocky planets or biological life. Fast forward to the 5 billion year mark on our clock. In a quiet sector of the universe, a localized cloud of this recycled hydrogen collapses to form our specific sun. Among the network of planets forming in the sun's orbit, the early Earth was a molten sphere of liquid rock dominated by massive volcanic eruptions. As the early solar system settles, a massive piece of lingering planetary debris collides directly with this molten Earth. The sheer kinetic force of the impact ejects billions of tons of glowing rock into orbit, which eventually cools to form our moon. While the surface remains violently unstable, a quiet chemistry begins in the deep oceans. Chemicals spewing from underwater volcanic vents interact with the cooling water, providing the conditions required to assemble the very first microscopic cells. Every stable feature of our planet we rely on today, from the tilt of its axis to the tides of its oceans, was forged entirely by these random, violent cosmic collisions. For the next 3 billion years, earthly evolution completely stalls. Simple, single-celled microscopic organisms hit an absolute biological ceiling. This changes with the evolution of cyanobacteria. Cyanobacteria are single-celled photosynthetic organisms that generate their own food and release oxygen as a byproduct. These microscopic colonies multiply rapidly, pumping massive volumes of oxygen gas into the primitive atmosphere. This surplus of oxygen enabled organisms to switch to aerobic respiration. Aerobic respiration is a chemical process that uses oxygen to break down food molecules, releasing significantly more energy than previous methods, and providing the fuel required to build complex, multi-celled bodies. Right as complex organisms begin to develop, the planet plunges into extreme climate stress. Earth freezes over entirely in an event known as Snowball Earth. Snowball Earth is a scientific hypothesis proposing that the planet's surface became entirely frozen at least once in its history. Immediately after this extreme ice age breaks, advanced organisms rapidly multiply in an event known as the Cambrian explosion. The rise of the animal kingdom was not a gentle biological progression. Global atmospheric pollution from oxygen and severe global freezing were the precise, brutal catalysts required to force complex life to adapt and survive. We now bring our focus back to the 10-minute clock. Remember our rigid rule. Every single second that ticks by on this scale equals exactly 22 million years of real time. We watch as millions of years blur past. Dinosaurs rise and fall, and early mammals spread across the continents. We finally arrive at the physical evidence of early bipedal evolution, seen in the fossilized remains of ancient hominids like Australopithecus. Australopithecus is an extinct genus of early primates that lived in Africa and marks a crucial step in the human evolutionary lineage. From there, a rapid, branching evolutionary sequence takes place. Multiple hominid variations, including Neanderthals, adapt and evolve across different environments before modern Homo sapiens emerge. On a 10-minute scale representing all of cosmic time, the entirety of human history, from our very first upright steps to modern civilization, occupies only the final fraction of the very last second. Humanity occupies the final heartbeat of a 14 billion-year odyssey. We are the specific result of a sequence of cosmic accidents and biological breakthroughs that allowed the universe to finally look back and observe itself. If you've made it this far, thanks for watching. Please consider subscribing to Deep Dive Daily, hitting that like button, and dropping a comment below.